Your model outputs logits, but you act on probabilities. We will turn scores into probabilities with Softmax in Python and make the difference feel obvious. Ever looked at a model's raw scores and wondered why a bigger number did not mean bigger confidence? That confusion costs time and causes bad decisions in pipelines. By the end of this video, you will know the difference between rank and confidence, how to convert scores into calibrated probabilities, and one simple safety pattern to avoid overconfident predictions. I'm Professor Pi, teaching AI foundations from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Models often give raw numbers called Logits. Those are just scores, not probabilities. Practitioners reach for Softmax when they need a shared scale across classes, so decisions, thresholds, and downstream logic make sense. Softmax solves the practical problem of turning arbitrary real scores into a probability distribution that sums to 1. So you can compare confidence across inputs, set thresholds, and measure calibration. Success looks like fewer blind trust mistakes and easier decisions when your pipeline has to defer, flag, or act automatically. At a high level, Softmax exponentiates shifted logits and normalizes them. Intuitively, exponentials amplify differences, and normalization turns the list into a pie that sums to 1. A tiny example with 3 classes already shows the power. If one class dominates the exponentials, it gets most of the pie. If 2 classes are close, probability mass spreads, and you know to consider alternatives. The weakness is numerical range and overconfidence, which we will address with temperature scaling and a fallback threshold. We will build a small sequence of toy snippets. First, we will show raw logits and their winner, then convert to Softmax probabilities. Inspect the top 2 mass, apply temperature scaling, and finally make a thresholded decision that can fall back to uncertain. This will keep the story clear and practical. Let's start with the raw model outputs. This snippet selects the top class from Logits to show scores are not confidences. We define a tiny label list called classes and their raw model outputs as Logits. The variable I finds the index of the largest logit using max with a key function. The print shows the winning label and its raw score, which can be any real number and shifts with scaling. Logits are not bounded and do not sum to 1, so they cannot be read as probabilities. The printed result shows the winner's score, reminding us this is rank only, not certainty. In other words, a winner with score 10 is not twice as likely as a winner with score 5. The numbers are relative and need conversion before we treat them as confidence. Next, we will turn those scores into proper probabilities with a stable Softmax. This snippet converts logits to probabilities with a numerically stable Softmax. We subtract the maximum logit into M so exponentials don't overflow, but relative differences stay the same. The list exps stores exponentiated, shifted scores, and probs normalizes them to sum to 1. The list pairs couples each class with its probability rounded to 2 decimals for readability. Now each value is between 0 and 1 and comparable across classes on a shared scale. The printed result shows calibrated probabilities per class you can treat as confidence. Practically, this means you can compare a class probability directly to a threshold or compute expected value across classes for a downstream cost. Next, we will inspect how much of the probability pie the top 2 classes hold. This snippet ranks probabilities and measures how much mass the top 2 hold. The list IDX orders class indices by probability from highest to lowest. The list top 2 prepares a readable view of the best 2 classes to reason about alternatives. The variable mass sums their probabilities, showing how concentrated belief is among the leaders. A high mass means the model is confident the answer lies within the top 2, even if not absolutely sure of the winner. The printed result quantifies that concentration directly. This is useful when you want to present a short list of candidates to a human reviewer, or when a downstream step can handle the top two, but not all classes. Now we will show how to soften or sharpen those probabilities with temperature scaling. This snippet applies temperature scaling to soften or sharpen Softmax confidence. The parameter tau divides Logits before Softmax, with higher values spreading probability mass, and lower values making it peakier. We recompute probs t at tau and compare the margin between the top two classes against the original gap. The variable calibrated gap reports how much the margin changed under temperature scaling. Increase tau to reduce overconfidence. Decrease tau to make decisions more decisive but riskier. The printed result shows whether calibration nudged confidence up or down, and by how much. Temperature is a simple and effective calibration knob when you want better calibrated probabilities without retraining the model. Finally, we will use probabilities to make a safe, thresholded decision. This snippet makes a decision using a probability threshold and an uncertain fallback. We reuse the top index from the ranked probabilities and read its probability p. The variable 3 encodes how confident we must be before committing to a label. The variable decision returns the label if p clears the bar, otherwise a safe uncertain signal. Raising thir reduces false positives but defers more cases. Lowering it decides more often but risks mistakes. The printed result shows a practical, calibrated choice driven by probabilities, not raw logits. This pattern is ideal for user-facing features and pipelines that need a reject option or human review for low-confidence cases. Mapping this toy flow to a real system is straightforward. Replace the tiny classes with your model labels. Run Softmax per prediction. Apply temperature found on a validation set, and gate decisions with a threshold informed by your cost of errors. The same steps scale from single predictions to batch scoring when you compute probabilities in vectorized NumPy or your model-serving runtime. Recap: Softmax turns logits into probabilities that sum to 1 and are comparable across classes. Use it when you need calibrated confidence, thresholds, or ranked candidates. Caveat: Softmax can be overconfident and sensitive to scale, so temperature tuning or validation is necessary. Next step: tune the temperature parameter on a held-out validation set to get better calibration and measure accuracy versus rejection trade-offs. If you want to scale, add timing and accuracy checks across a larger corpus or integrate a fallback human review. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.